Hello, everyone. Please welcome our next speaker, Ivan Čuljak.
So, hi, everyone. The topic of this talk is making the cloud event-driven and orchestrated. Oh, I need to have a timer. Wow, this feels like a startup competition. So, who am I? My name is Ivan Čuljak. I'm a .NET freelancer from Croatia. The main stuff I do is some distributed systems on Azure and Xamarin Forms apps. So I've been developing serverless stuff on Azure for, over 2.5 years. So when I say developing, I mean someone really paid me to do it. For the last, a year and a half, I've been on a quirky project where we are using and misusing serverless on-prem machines. We've basically took PowerPoint, the desktop app, and made it scalable in cloud. So we have a scalable PowerPoint as a service. And it works, it's stable, it's not crashing, but it took a while to get there. So during that, we've tested, deployed, crashed, probably done everything that you shouldn't do with serverless. But now we know a whole bunch of things, how to do it, how not to. And, I'm a guy with an antivirus on a Mac. So, yay, Windows developers. So, to start with, code examples don't make much sense because I had to cut them to fit on the slide. So, bear with me, they are abstract code. The second thing is, this talk is mostly about serverless, and serverless mostly on Azure, although the concepts can be used even if you don't use Azure, even if you don't use cloud, even if you have a multi-cloud environment, if you want to combine on-prem, etc. But if you don't need serverless, something else might be better for you, like actor models and Akka frameworks, or Akka.NET if you're a .NET guy or a girl. So, second of all, when people talk about serverless, people tend to first think of Lambda. Lambda is a function as a service. Serverless isn't functions as a service. Serverless is so much bigger. It basically describes an infrastructure of a service that can be scaled. If you ask the marketing department, it can be scaled instantaneously and infinitely. Well, in reality, it's not. Serverless is great when you really need it. But if you don't need it and you just want a really cool new shiny tool in your tool belt, it might cause you more problems than solutions. Please do come in. Okay. Serverless is being marketed as something that's really cheap to use. And it is if you use it every now and then. But if you have enough load to keep the serverless instances always alive, you might be better off with a virtual machine because it might be cheaper. Another popular thing to do for the last 2 years is let's take a monolith, break it into microservices. And when microservices were a thing, there was an anti-pattern called nanoservices, when you would break them into 2 small pieces. Well, those are functions. They are nanoservices. So if you start breaking your monolith into something really, really small, you're going to have a whole lot of work, and you might do a whole lot of damage to you, because on some projects where I were, people would break all the methods into so small pieces that instead of querying the database only once and sharing the information between a whole bunch of methods, each method, meaning each function, went to get some data from the database. And the system worked so much slower at the end. The coolest thing is that, like the meme with C++, functions allow you to shoot yourself in the foot. And there are currently no tools which would tell you, hey, you just created an infinite loop. You've just created something that will time out and you'll have no idea why is your process crashing, and so on. The easiest thing to compare serverless development with some real-life examples might be a console app. So let's start building one. On the left-hand side, there's a single class with a single method writing hello world. It's a popular thing to do. The second step might be to add some more methods to our single class. So we are developing something. At the end of the day, we end up with two classes. Each class has a single method. One method is check balance. That method, after it's done, calls pay invoice. So a real life example. Notice that all those methods have a return type of void, so they don't return anything. When you pay the invoice, the cool thing to do would be to, update the UI and send an email that the money went through. And here comes the first problem. Those methods are handling stuff outside of their scope. So why is that a problem? First of all, you get spaghetti code. It's not a problem on the example, but once you start having tens of thousands, hundreds of thousands lines of code, and you have multiple developers, some developers quit, new ones come, it's gonna be hell on you, because no one will have any idea why is an email being sent from somewhere. And you're gonna have a hard time to debug it, but first you need to find it. And with all the tools, so if you ask me, Visual Studio is the best IDE around. It has all the bells and whistles, but let's forget the fact that I really need a desktop machine with a bunch of cores and a bunch of memory to run it. But even Visual Studio can't help you to find all those things. So you need to buy some extra tools, paid thousands of dollars per year, just to get a graphical representation of what is your software doing, what's the workflow. And you could have had all of that in a single place. So what do we do now? On the left-hand side, there are two red lines of code which do stuff that isn't really necessary for the method to complete. So we're gonna introduce some events. Instead of those two lines, we have an imaginary class called Event Center, to which we're gonna send an event called done. So meaning invoice is paid, I'm done, let's get over with it. That's easy to solve in a console app running on a single computer, but how do you solve it in the cloud? Well, if you're on Azure, there's a cool service that's been out of the preview for over a year called Event Grid. Event Grid is a serverless service meant to connect all your apps, all your infrastructure, not only throughout your Azure cloud, but it can interconnect with stuff on AWS, Google's Cloud Engine, Oracle's cloud. You can even use it from your on-prem infrastructure. And the idea is that you just start pushing events into the event grid. Once the event comes to the event grid filters it, because you can set filters there. It's kind of similar to an enterprise service bus. You can set filters there and see who has subscribed. And when the event grid gets a list, where does it need to send those events, it will just push them. And that's a really cool thing. So unlike service bus, unlike queues, this is a push-push situation. So someone pushes to event grid, and then event grid pushes it further. The cool thing is there's even a dead letter, sort of a queue. Event grid can retry for a certain amount of times to redeliver the message. But you need to worry to take care of a condition. It gives you a minute. So when event grid tries to deliver something, it gives you a minute to return either a 200 OK or 202 accepted. If you don't deliver it in a minute, that means that the delivery failed. And that's a problem. What if your logic is to start some long process on that event? That's something that you need to handle, and we'll show later on how to handle those situations. So the second problem is that the methods that we've shown have some business logic that's irrelevant to them. So why is that also a problem? Well, first of all, your code still isn't clean. You're doing stuff that's not supposed to be there. Another problem is that if you set timeouts for certain methods, they might time out because they are waiting on other stuff to finish. For example, a new developer comes and you have a check balance method, and that new developer says, hey, this should finish in like 2 seconds, and he sets a timeout, but he doesn't know that check balance tries to pay for something and then tries to update something. So what are we gonna do? We're gonna make the code, well, a bit more complex to make it more simple. We're gonna introduce another class, which we can call a function orchestrator. And the whole business logic will be sitting there in, let's say, a single method. So instead of calling pay invoice from check balance will do only, well, checking the balance. And the orchestrator method will be calling the first method, the second method, the third one, and so on. So just a warning, when we talk about orchestrators, these orchestrators have nothing to do with containers. So forget containers, forget Docker, Kubernetes, anything. We are orchestrating business logic and serverless functions. Okay, so how do you do it in the cloud? Well, this is where it gets interesting. You need to create yet another, either service, an endpoint, a function, something that will keep your whole business logic. But the real question is, how do you call those other methods? You can start, if you have a monolith, you don't have this problem because you're just calling another method. But if you're using serverless, you need to ping those other functions somehow. The easiest thing to do is actually to get an HTTP client and call them, and then wait for them. That might be the problem, because functions have a timeout period. It's usually 5 minutes on Azure, although you can extend it to 10 minutes. It also timeouts after 10 minutes on Lambda. So if your process is taking longer than 10 minutes, you have a problem. So waiting for them isn't the best choice you could do. That's the third problem. So the orchestrator is waiting for all the other methods to finish. In your console app, that's also a problem, because you're blocking either a thread or something. While you're waiting for something else to finish, you're blocking some resources. If we talk about the cloud, blocking some resources might mean that you are paying extra money. Because if a child function is performing some stuff for 5 minutes and the orchestrator function is waiting for it to finish, you're paying twice for 5 minutes. And at the end of the month, you end up with a nice bill, because functions and serverless aren't so cheap as they seem at first. So, and another problem, it might time out. How do you solve it? Well, in .NET, it's really easy. You make them asynchronous, and you just await for them. So what does await do in .NET? It makes a continuation point in your code. So when you await something, it creates a continuation and releases that thread. So the execution on that thread can continue, and once the called method returns something, it gets back and continues the execution of the caller method. So basically, you're not blocking something while you're waiting for something else. You can't do it easily in the cloud, and that's why we introduce queues. So when you need to wait for something that you don't really want to actively wait, you send a message through the queue. The child method or function gets that message, does some job, and now here's the problem. How do we return the message that, well, we're done? And there's another problem. It's easier to say just, hey, I'm done, than sending back some sort of a result. especially if we're talking about something that's not JSON serializable, because you can easily add messages containing JSON serializable data to queues, but you can't add a binary stream. And even queues, the messages in them have, they have a limit on how much payload can you send. So that's a challenge to do. We'll see later on how can you properly solve it. But one cool thing is if you start using service bus, so it's not only Azure service bus, any enterprise service bus will allow you to do something that mimics transactions, meaning that when you send a message down the line, you can set something called a reply to session ID. And then the child will get that information, and when it has something to return, it will just return the message and specify a session ID. And on the calling end, you might set an awaiter for a message with that specific session ID. So you get asynchronous communication over a distributed system where you have no idea who's listening on the other side, and it just works. That's why you should use service bus queues over storage queues, because a whole bunch of people start with storage queues, which just add JSON files to blob storage. And well, they do the trick, but they are not as powerful as you can get. Okay, so the question is, why are we mixing events and messages? First of all, there's a difference in concepts. Let's take my wife, for example. So after she's done with making the dinner, she has two choices. She can say, the dinner is ready. And that's it. That's an event. She said the dinner is ready. She shared the information. She has no idea whether me or the kids heard her. And even if we heard her, she has no idea what are we going to do with that information. We might just ignore it. The important thing is that with an event, she shouldn't care. But if you use a message, that's a command. So in real life, that would mean my wife coming to me and then to all the kids and saying, get your ass to the table now and eat. That's a message down the queue. And she might expect a response, seeing us that we actually sat there. So on Azure, you have the event grid, you have the service bus. Except for the difference in concepts, there's a huge difference in how they work. Since event grid is a push-push solution, it gets things done much faster. Because service bus is a push-pull solution, meaning that you push something to the queue, but then there's something on the other side that needs to pull the messages from the queue. And although when you write the code, you can set an event trigger. Hey, trigger this when there's a new message in the queue. But in the background, it actually has a timer that loops and checks if there's a new message. Event grid is really scalable. Service bus, not so much, but it's enterprise grade. And it allows you to do really cool things like duplicate detection. So you can set it a time frame where it will reject all the messages that are duplicated. And that's cool because I don't need to take care of that. So whatever it gives me that I don't need to take care of, it's really cool. Okay, now let's start with more complex problems. Where do we store our context of our results? So if we're talking about a simple method, let's say something that needs to be done each day, something that updates the database with 2 steps, meaning first step, download a file, an XML if you'd like. Second step, import it to the database. There's no data that you need to share. There's no context. It's a simple solution. But what if you say, hey, pay to that account $1,000? First of all, you have the account number, you have the amount you need to pay, and then you'll get some responses from the methods you're calling. For example, check balance shouldn't return true or false. Check balance should return the balance, and then you need to compare them. Okay, so if your code is running on a virtual machine or something that doesn't go to sleep, and you can store the context in your memory, you might ignore this problem. Why did I say might and not that you can? Because what if your virtual machine restarts or your internet connection breaks? You're doing a transaction that's really important. So in that case, well, event sourcing might do the trick. But who wants to implement event sourcing? It's not really a walk in the park if you want to do it correctly. So how do we solve it? First of all, here's the problem. We want to use the return value from the first method, from the first call, as a parameter to the third one. How do we solve it in the cloud? There's a really, really cool thing called Azure Durable Functions. So Azure Durable Functions is a framework built on top of functions. And the coolest thing is it's available on, the durable framework is available on GitHub. You can run it on your machine. So you can have your own durable framework functions thingy on your laptop and enjoy it. So what does it do? It basically allows you to execute long-running tasks by allowing you to easily orchestrate all your methods that you've broken into smaller pieces. And out of the box, it comes with event sourcing, meaning that whatever it does, it will be recorded immediately on the storage queue. The storage queue is a simple one, but it's really cool for this. So even if your durable functions fail or something happens, your state is saved there. What does it give you also? So remember how functions and serverless are being charged per usage. You get charged per each second that you use it. Durable functions allow you to not be charged while you're waiting. So instead of doing all the mumbo jumbo with queues and sending data back and, well, making a circus out of your system, you can just write the code as you would on a single machine. You can await something that will be executed in a data center on another side of the world, and it will just get the results back, or an exception. That's also cool, because you'll get an exception with the whole stack trace. That's really cool, and you can do some decisions on it. Okay, so now, come on. Now let's forget about the console app, and let's move completely to the cloud, except for those, well, remaining services on-prem, because, well, we need to use them, and we need to somehow connect them to serverless. Challenge is using something that's not a function in your Azure. Why? Well, durable functions were meant to orchestrate functions in a single app. So whenever you want to call something that's outside of them, you need to figure out how. For example, you might be calling another function in another function app. You might be calling something on a container. You might be calling something on AWS, or you might be sending something down the queue to your on-prem. So why send something down the queue to your on-prem machines and services? Because you don't want to expose them to the public. And that's the beauty of Service Bus, because it allows you to firewall your whole on-prem system, and they will connect to Azure Service Bus instead of Azure connecting to them. It's a really cool solution. And you can just keep adding stuff without needing to worry about service discovery, about firewall rules, about anything. Okay, so how do we use stuff that's not a function using durable functions? We might do HTTP requests and wait for them. Why could we wait for them? Because a durable function can start a whole bunch of other functions. Each of that new function has either 5 or 10 minutes, depending on what did you set for it. So we could be waiting, and we could be charged for that. We could trigger an event using event grid. and that other something would start working, or we could add a message to the queue. The question is, how do we get the results back? And here's a wonderful thing. Durable functions have something called an external event. And you can just say, I want to wait for an external event. And you give a name to that external event. And you set a type which will be returned. It needs to be JSON serializable. So what does this do? It generates a URL, a unique URL with the ID of the current execution of your orchestrator. So when you send something down the line, you just send the URL it needs to be called. So when that something is done, it just needs to call a simple URL and pass the results. That's it. You've connected something with not much problem. It takes 2 lines of code to do it. And, well, I feel the pain for this because before durable functions came, we actually built our own orchestrator. It took a few months. It's not even nearly extensible as this one is. And although it's working fast, it's working, it's not crashing, so it's reliable. It was a pain to build it, and it would be a much bigger pain to maintain it and extend it. So this is something that really allows you just to write distributed code as if you were developing it for a single machine. Okay, this is a neat feature. When you want something fanned out, it's not really a problem, meaning that you got a request, and then you want to spawn a zillion of other requests. You just use a for loop and send a zillion other requests down the queue. That's easy. But how do you wait for all the responses? And what if in a single of those pipelines there's an exception? Anything. If you do it the old-fashioned way, you're going to have trouble. And it's going to be really fun implementing it. Because if a function fails, a regular function, no one knows about it. It's like when a tree falls in the woods and no one's there to notice it, did the tree fall? So what you need to do is not only call other functions, but implement some timeouts, check, well, Redis is the fastest thing to do, so you constantly update the status of the execution in Redis. You do wonderful things to do something that should be easy. And this is what you get with durable functions. All you need to do is first create a zillion of tasks, like you would do on your machine. And then all you need to do is await them all. Say, when all pass a list of tasks to process, that's it. The durable orchestrator goes to sleep. When all of them are done, it will continue the execution. That's all you need to do, 2 lines of code. It's really wonderful. If anything fails down the line, you will get a notification. Okay, so now let's start with something interesting. A shark comes along. It's all the underwater cables around Ireland, and your data center doesn't have internet connectivity. What will you do? Okay. Durable functions can sort of handle it. So durable functions don't have a Geo Distributed recovery plan, meaning that you need to deploy them to each region where you want them supported. Durable functions depend on the storage account. And the storage account can be geo-distributed. So what you can do is you can either have a bunch of durable functions implementations in each region, and each one of them can have their own storage account. That's the simplest thing. But if something fails, you won't have any data. Another thing to do is, well, have the storage account geo-distributed and have multiple durable functions point to the same storage account. That's kind of cool, but the problem is if durable functions in a specific region fail, although there's data about it in the storage that's available everywhere else, there's nothing alive to continue the execution until the data center gets back. So you're gonna have a problem unless unless you start double tasks. So when there's something to do, you can send double requests to two regions or more and set a single request as a primary request and set all the other ones as secondary, meaning that they will wait for a certain amount of time before they check whether they should start executing or not. That's something that you need to handle manually, but since you're using durable functions, it's relatively easy to implement. Okay, storage is geo-distributable with a few clicks. Just click through the UI, the web UI, or you use the code, the shell to handle it. Databases are, well, mostly the same. You usually have a master database and active and passive synchronous and asynchronous replicas. But again, that's not something that you should be manually handling. It's something that you can just click your way through. But all the other services have a problem. They aren't meant for geo-distribution. They aren't meant for a recovery plan. So although it's really unusual for a whole region to go out, so although you AWS people probably remember the S3 failing, and because of it, some Microsoft services failed because Microsoft bought some startups which were running on AWS. But as far as Azure is concerned, there weren't any major downtimes unless you use Azure Active Directory. Anyone uses Azure Active Directory? Good for you, don't use it. Okay, so what do we do then? There's a neat service called API management. It's basically a proxy in front of everything you own. Why is it so cool? You can expose APIs through API management, and those APIs can be, well, anywhere. You can have parts of the endpoints on-prem. Part of them could go directly to Event Grid. Part of them could go to a platform as a service, something, or on AWS, the EC2 or the something sail. No one uses that. Light sail. Thank you. Okay, so why is this cool? Because it's geo-distributed. So meaning when you hit it, when you try to hit it, you'll hit the nearest region, unless that region is down, when in that case, your call will be rerouted to the other nearest region. My dearest feature of API management is throttling. So you can set levels of subscriptions, for example, a bronze, a silver, a gold. And then you can set for the bronze one that there might be maximum 5 parallel requests. So instead of you developing that, you've just set a number. And it's so beautiful because you can do different levels of subscriptions. Another really cool thing when we talk about serverless and event-driven is that, well, before summer, in order for you to start something that's serverless, you were supposed to have an API that's constantly alive, in which case we would use a platform as a service. So a call would go through the API management. It would be accepted by an API, which is basically a facade, and then it would be sent through the event grid or the queues. What you can do now is go from the API management directly to the event grid, meaning that you can cut a single one of the pieces of your system. So a request comes, it goes directly to the event grid, and then from the event grid, it can go directly to a storage queue, meaning that you've got something to process. You don't need to worry about any resources. Since the request is in the queue, it will get processed at some time when your resources allow it. And that's really, really cool. And it's stable. And since Event Grid has a retry policy, you can be sure that something will be added to the queue. But one thing to worry about, it's not a silver bullet, because if you want that kind of a workflow, your API, or at least those endpoints, shouldn't be returning any data. So if you forward the request to the Event Grid, the only thing you're gonna get back is, hey, we're okay. That's it. So it's not really set for gets or something that needs to await the processing. So how do we use it? Our APIs mostly have a single workflow. You send a request, and we respond with a 202 accepted. And you pass us the webhook to which, when we're done or something fails, we call that webhook and send all the results there. In that way, nothing awaits for anything. So your caller, it could be a web app, it could be anything else. Your caller is done in 50 or 100 milliseconds. And once the process is done, and well, on one of the projects, some processes take 20 minutes. So there's no sense in waiting for them. Once it's done, it calls the webhook and we're done. Okay, so that's basically it. There's a whole bunch more to talk about, but well, it's early, lunch is nearing, so I don't want to stop you and make you miss the lunch. If you have any questions, if you have anything you can ask now, you can ask during the day or tomorrow. And well, thanks for listening.
10 minutes.
10 minutes?
Yes.
Do you want me to sing you a song?
Any questions?
No. Yeah.
Thank you. Does the API management then become the single point of failure?
Yeah, definitely. Although Azure is distributing it over all the regions. So yeah, it's a single point of failure, but haven't heard of it failing not once in over 4 years I've been using it. So it's an enterprise solution, and it has an enterprise price tag. So in a development subscription, which you shouldn't be using for production, the price is around $60 per month for a single region. When you go out to production, we're talking about $200 per region. And if you want a whole bunch of parallel calls, it only goes up. So that's the most expensive part of a system where you're trying to save money. Because, well, basically, why you went to serverless is to try to save money.
Thank you.
Any more?
Nope.
Going once?
Going twice.
Going twice?
Sold? Thank you.
Thank you.